So thanks, Jatan, for joining us for this week's GISS lunch seminar. Jatan comes to GISS from Lamont. He's currently a postdoc research scientist there, where he works with Park Williams and Pierre Jantine and develops physics-informed machine learning models to study wildfires in the western United States using multiscale climate, vegetation, and population datasets. Before joining Columbia University, he was a visiting assistant professor of physics at Brown University, where he taught statistical physics of inference and deep learning. And before that, he graduated in February 21 from Brown University with a PhD in physics, where he worked at the intersection of particle physics, astrophysics, and probabilistic modeling, and focused on phenomenological searches for dark matter. So, Jatan, it's great having you here, and we're super excited to hear your talk. You can go ahead and start.
Thank you for a lovely introduction, Karen, and thank you so much, Marcus and Karen, for inviting me. And I will, I'll try to keep this informal, so please stop me at any point. I'll focus on just one project, not to overwhelm you with information, and I feel like having a back and forth will improve, I guess, both our experiences. Okay, and I'm going to be talking about the work that I've done so far in my postdoc, which is modeling multiscale climate vegetation fire relationships with machine learning. Since it was mentioned, though, that I did my PhD in physics, I should probably explain what's the connection between dark matter and fire. And the connection, as far as I can see, is stochastic processes. So on the left is a picture from competitor. It's the European Space Agency's Gaia mission, which aims to map the positions and velocities of about 1 billion stars in the Milky Way. And this is a map of the Milky Way that has been reconstructed based on these data. And on the right is a map from VIIRS of all the total fire radiated power in 2020. And so besides the mole-wide projection of this to the sphere, what I basically did was in my PhD I used a stochastic process model with some Bayesian twist to infer the dark matter density based on how stars are moving and assuming some dynamical model. Whereas in this case, for the fires, I focus in particular on the western United States, and I'll be talking about how I model fire frequency and burn area. In at least the frequency case, I use the same in homogeneous Poisson process. And the talks and the results that I'll discuss in this talk are in this paper. I should probably minimize this.
You can close it.
Or I can close it. Mm-hmm. Oh yeah, perfect. Are available in this paper, which should be in GMD any day. There's some minor line revisions, but should be at GMD. In any case, it's on the preprint server, and it contains all the results that I'll be presenting. Most of the results, because there's few results of work in progress. And I should just highlight that although I'm giving the talk, my research has been greatly enriched by several awesome collaborators. Park Williams, who's now at UCLA, Carolyn Zhuang, who is Park's student, and who's prepared the data set that I'll be using, the fire data set, that is. Winslow Hansen, who used to be an Earth Institute postdoc, and now is at the Carey Institute upstate, and Pierre Jantine. Okay, so focusing on the Western US, I want to say that the data set that I'll be using here is the Western US MTBS interagency data set, which contains all fires greater than a kilometer square from 1984 to 2020 on monthly timescales. And the locations for all the fires in my data set can be seen in these black dots underneath all the layers in this figure on the left. Above these dots, however, are at the first scale, these are ecoregions. These are Bailey's ecoregions, which are rough sort of relationship between a rough sort of region which has homogeneous climate and vegetation relationships. That's strictly not true, but it's a level of coarsening that we found useful for showing our results. And I've shown about 18 ecoregions here. The other, at the highest spatial scale, however, we have forests in green, deserts in yellow, and plains in gray. And again, I should say that forests doesn't just mean forests. Like even in forests, there are other vegetation types, but these are the areas where forest is a dominant form of vegetation. And we do this sort of organizing just so we can have an idea, even at very coarse scales, about the annual frequency in blue and the annual area burned in red of the temporal trends from 1984 to 2020. And one thing that clearly stands out is, especially for forests, or what I call forests here, there's basically an exponential increase in area burn. And this is mostly driven by fires in California. So I could tell you about, like, all different kinds of fire suppression cost metrics. There's some billions of dollars attached here in terms of costs. But I think even from a scientific perspective, this is just a very striking relationship that needs to be studied from a modeling perspective. If numbers interest you, so the increase is about 1,000% of the running average over the past 40 years. From a resource allocation and planning perspective, what is also interesting is if you look here on the plot on the right-hand side, and you look at forests and the wildfire area. So these are the forests are in green, and all the wildfire area is in maroon. You see that not all wildfires occur in forests, and in fact, a lot of these wildfires occur in something which is known in the literature as the wildland-urban interface, or WUI for short. And so that means that you have these locations across the western U.S. where people are moving in, they're setting up new settlements, and that's where you have a lot of the fires sort of expanding from forests into this WUI. And so from a planning perspective, you'd want to know like what is the fire risk, and so you can arrange your settlements accordingly. Thinking more abstractly about this, we can think of this as a fire triangle at multiple scales. So this is the multiscale behavior. And so this could range from the microsite, which is like the site of an individual canopy. And so there you can think of fire as an interaction between these three elements, which is you need oxygen, you need a flame, and you need heat. So you need fuel and heat, and that produces the flame. And this is on the order of seconds on the temporal scale. If you go to order of days, you need fuel. So this is over a patch of land. And you produce fire behavior by the interaction between weather and topography. So it turns out that fires spread faster on slopes. And for instance, at higher elevations, this is correlated with drier weather. So that correlates with high risk. And so this describes fire behavior on the scale of a wildfire at the order of days. And then on decadal scales, this is something that you'd want to study climate relationships. And this is the interaction between climate ignitions and vegetation, and this describes a fire regime. And each of these cases I've described, or what Parisian and Moritz have shown, is that there's some feedback loops. And a very important feedback loop, for instance, is if there's a fire in an area, and there's repeated fire activity over timescales, and the vegetation has adapted to this sort of fire climate relationship, then if you have drier weather, then the vegetation that follows after a fire would naturally not be, or if the fire frequency increases, the vegetation that follows would be not adapted to this new regime. So you'd want to account for the fact that the sequence matters in terms of vegetation progression. On the right-hand side, what I'm showing is, and so I should also say that on the red arrows show the scales at which I'll be focusing. So this is about individual wildfires and at the monthly scale. And on the right-hand side, I'll show that, well, when you think about fire relationships in space and time, you also think about what variables are important and what variables in terms of building the fire model, but what variables should you output so that this output is useful. And so in this case, the weather the fire variables that I'll be using come mostly from remote sensing, including some of the fire data set, but also from like National Land Cover Database that gives me the vegetation. But also in terms of why I'm producing this model, it'll be important for all kinds of planners from land management agencies to at the regional scale. You'd want to plan for the risk as to where to build housing and so on. I should also mention that the relationship between climate, vegetation, and fire has a stochastic element, and this stochastic element is true at two levels. So one is, of course, fire is a stochastic process in itself, so ignitions are stochastic, so they're random. But also, even if you have the perfect fire conditions, not all fires will be the same, given the same conditions. So there's this dual stochastic nature to this, which I'll aim to model with stochastic modeling. To one final slide to just give you a sense of where I'm coming from, and I promise I'll get to the model after this. Is to sort of situate, because I know that this some of the having read a few papers from folks in the audience, I know some of you have worked on statistical models, whereas others work on process-based models, and I wanted to situate my own research in this sort of landscape. And so on the statistical model side, the name of the game is simple, so to speak, which is you take a statistical distribution for frequencies. And this, I'm showing results from Westerling 2011. And they focus on just one region. It's the greater Yellowstone ecoregion. And so what they did was they modeled the frequencies at the grid scale level, not too unlike what I'll be showing. And for each of those grid scale frequencies, every time they had a high fire probability, they simulated using a Pareto distribution the size of that fire. So you do this modeling in 2 steps. You first predict the fire frequency, and then you predict the fire sizes. And this goes to the 2 stochastic elements of the fire that I was talking about. The more modern version of this looks like from this paper that was published last year in GRL, which is something that I feel is you will see a lot of papers coming out this way, which tries to predict next day fire spread using a convolutional neural network. So, but what does that look like? It means you take a grid data set of weather, vegetation, and all kinds of fire-related variables, and then you give it, and then you train it on multiple over multiple days on observed fires in the past. And so once you learn these statistical relationships, what you do is you're able to train this model, or you're able to run this model in real time and then predict, as they did for 3 days in August, like the fire probability at the grid scale level, and then they compared these results. So in this case, they used another like temporal sequence model called the LSTM, and they compared it to the fire weather index, which is something that fire managers have been using. And they found that with the LSTM model, they're able to get higher resolution based on the statistical relationships that they studied, as compared to the fire weather index, which is, you can think of this as an approximate physical relationship. So the spatial scale that these rely on are at the kilometer and the regional level, and so they could be at the kilometer scale, grid scale, to all the way to the regional level, and the temporal scale is about daily to a monthly. On the other hand, you have process-based models. So this is the wire diagram from Lee et al. 2012, where you actually include the physics of the fire. So you have an ignition model, for instance, and this relies on lightning frequency. And you also have a population density parameter, or like a parameterization, which affects both the ignition as well as suppression for fires. And then there's vegetation, there's weather components, and there's, at the end of the day, the heart of the fire model relies on semi-empirical semi-empirical physical relationships between fire observables, in this case counts, burned area. It could also be biomass burning, and so the different species that you produce. And so these relationships are something that are, I'm not an expert, but I understand that these are hard-coded. And in some sense you could train it, but these are present in the model. And naturally, both have their strengths and weaknesses. And again, I won't go into which one you should prefer. What I'll try to say is that I think machine learning offers, or let's just say principal statistics or statistical modeling, in this case with machine learning, offers a way to sort of bridge the gap between these two regimes. How do I do this? Well, in this case, I'm just going to be talking about a statistical model, or rather I should say a stochastic machine learning model for Western US fires. And this is the work that has been published, and I'll go into. So what do the fires look like in this grid world? They look like these two dots that I've shown here. The spatial resolution of the grids that you see here is 12 kilometer by 12 kilometer. The temporal resolution is monthly. So you have a total of 10 million grid cells. So this is 32,000 over the Western United States in space times about 400 in time. So these are 400 months between 1984 and 2020. And the total number of fires are 18,646. So one thing that should already strike you is that fires are an incredibly rare process. And this will inform some of the techniques that you use during the machine learning process. And just to give you a sense of what these fires look like, I plotted two of the biggest fires in this data set. The blue is the Dixie fire in 2021, which burned about 2,000 kilometers square, or about 500,000 acres. And the August complex fire in 2020, which burned about 3,600 kilometers square, about 1 million acres. And both of these happened in California. And so one of the things that should strike you right away is that if you have a big fire like this, first of all, it's rare, even among the fires, which are a rare process. And so that is one thing. And the second is, if you have a big fire like this, and these are the fires that you're interested in, one of the things that you'd want to do is you'd want to account for the fact that these spread across multiple grid cells. So you need to account for some way in which how you average the weather and the vegetation predictors across these grid cells. And so what I do for just fires in general is I include about 51 predictors, potential predictors. The actual number is fewer in the model, and I'll get to that at the resolution indicated. And I consider effective input predictors for modeling these large fires, which are an average across all, or which are a weighted average, weighted by the fraction of burned area in those grid cells across all the grid cells that are intersected by the fire's perimeter. And what are some of these variables? You can think of fire as something that is caused by hot, dry, and windy conditions. And so you have Tmax, which is just the maximum daily temperature. You have the antecedent version of that. So I consider like averages in the past month. So 2, 3, 4 months. I also consider, in this case, the X-day maxima in a month, just to include the fact that some in some months, especially in recent memory, there have been heat waves. So how do you account for the fact that there are heat waves, and the mean state of the month could differ from the X-day maximum? So you include the X-day maximum, or the monthly mean of X-day maximums, and then you also have the minimum temperature and the maximum corresponding for that. You also have, for dry conditions, you have atmospheric aridity measured by vapor pressure deficit, and similarly antecedent vapor pressure deficit. You have precip in the fire month, but you also have antecedent precip, just because it correlates with drought conditions. And then you have snow water equivalent, which measures the snowpack, which is also an indicator of drought.
So what's the effect of these variables being like not entirely independent? Like if you just like doubled up on a variable, would that just make it like doubly important for the training of your algorithm?
So double up in what sense?
Like, let's say you just like duplicated one of these input variables and like fed it into your training. It would just sort of like double the impact of that variable on in terms of the importance of what it's trained on, or
well,
I'm thinking of that as like a corollary to these things not being entirely independent.
that's right, and yeah, no, I think that's a good point, and I think I want to just distinguish between correlated variables while training the model and producing a certain result, and correlated variables when inferring their importance. And in machine learning, these two things are, for better or worse, decoupled, right? And so if these are correlated predictors, and this is a good exercise, which I haven't done, to be honest. Like if I just duplicate VPD, maybe add some noise, what happens? I think the machine learning model itself, because it has this, it removes correlations, and or at least at the first pass, what I do is I remove the correlations, or I remove the correlated variables. Like I ensure that this 51 number reduces to 28. So there's a filtering step. But at the importance level, which is what I'll talk about using Shapley values, I think that method will fail spectacularly because it won't be able to distinguish between VPD alpha and VPD beta. And so this is something that we should talk about in the limitations of machine learning models as such. So there's the hot and dry, and the indices, which are the fuel moisture, the 1,000-hour fuel moisture, which is a climate-derived moisture balance index, and the Fosberg fire weather index, and similarly the maximum of that index. Similarly with wind and lightning. On the vegetation side, I consider forest, grassland, shrubland variables. These are derived from the National Land Cover Database, and this just show this variable is just a fraction of each of these land cover types in that grid cell. The biomass is something that we added later on because we felt that the model did not have adequate spatial memory or like had a spatial distribution because these fraction variables were just fractions and not the absolute vegetation. So we added this static above ground biomass variable for just 1 year. So it's a static, just to give a sense of like where the biomass is distributed. But this mostly matters in space. In time, it turns out that for arid and semi-arid regions, there's a memory effect. So if there's high precipitation in the previous year or in the 2 years prior to the fire season, you'll have more vegetation, which will be, when exposed to dry conditions in that fire month, would burn more. So you'd want to account for that temporal dependence as well.
But also works the other way. If you have prior is weather conditions, then that could be also that could oppose, for example, the development of a wildfire.
In certain cases, that's also true. Yeah, you're right. I mean, it's not universal. And again, in the explanation plots that I'll show, it just happens that on average, the effect of more precipitation in the lag 1 and the lag 2 year turns out to be more fire. There are cases where it prevents the fire, but in most cases, it promotes the fire. You also have topography variables, which is slope and the southness aspect of slope. And then you have some of these human-related variables where it's the number of campsites, distance from campsite, distance from nearest road, the housing density, the population density, and in this case, this is the distance from an area of population density, 10 people per kilometer square. It turns out that this is actually, the model is not very sensitive to population density, but it is sensitive to distance from population density.
Do you have an index there that's associated with wind speed, for example, surface wind speed?
Well, so we do include wind, but the Fosberg fire weather index, it's an index of hot, dry, windy weather. And of course, the problem with including these indices is that they've worked well for certain regions. So the Fosberg fire weather index works very well for Southern California, where you have the Santa Ana winds. But I mean, over the Great Basin in Nevada, not so much. So this is.
So if you have all of these other variables,
that's right.
Those are as derived indices. Those indices are derived from the other variables.
That's right.
What's the value in including all of them in the model?
It's a good point. In an ideal world, the model would just be able to create the best fire weather index. And I would, in terms of interpretability, I would say that it does, except that the current recipe for the fire weather index is also one of the components of the new fire weather index. That's allowed.
It's counterintuitive.
Yeah, I mean,
but
sure. Yeah. I mean, yes. I mean, it's not a...
Like, why does it need it if it's derived from the other variables that you're also feeding it?
Yeah, it turns out that the results that I'll be showing, or that I will show, are like the optimal results. So you do this ablation study where you remove like a chunk of the variables and you see what happens. And this is the one that performs the best. Now, yeah, okay, even if it performs the best, then the natural physical question is, why does it perform better? The why is not a part of this talk. But it's an excellent question, and I think something that, if you're building the next generation of like process-based ML models, it should be a part of that recipe. Yeah.
I have another question. So with these predictors, what would it take to make your model a global model, not a regional model?
Excellent question. So it turns out that, and again, maybe this is for like a full-scale discussion after, but machine learning doesn't work very well so there are certain regimes, so to speak, right? So here I'm training across all, or I will show is that I will be training across, I'll be introducing this model and be training across all of Western US. Turns out that you'd want to sort of condition on vegetation. You'd want to condition on certain seasons because the relationships differ. And this is just a first pass, what happens when you just run everything. So when you go to the global scale, for instance, I should also mention that the another confounder would be natural versus human ignited fires, right? So even if you include all of Western United States, the East is mostly human ignited, especially in the Southeast, whereas the West, besides California, it is 50-50 in terms of natural versus human ignition. So how to account for the fact that if you, in principle, and I think this is an exercise that I'd be very interested in doing, just take this model, like the model framework, and feed it data from the entire world. And it'll give me some results. Do I trust these results? To be seen. But I just want to flag already that the question that you're raising is a very important one. And I think, again, we need to be thinking more in terms of regimes and training because, yeah, you'd want to...
So just a quick follow-up. So instead of creating a global machine learning model, would it make more sense to tile different regional machine learning models to provide like a global prediction?
If I had to put on my machine learning scientist hat on, I would say you'd want to learn what these regimes are using a machine learning model, and then have this thing where you teach like a central like sort of classifier to be like, depending on the regime that I find this part of the global regime, global fire regime, and then choose that particular model for it. So you'd want to build a whole computational model for it. And but who knows? Like maybe the previous generation of scientists, when they were building like physical process-based models, they were just like, this looks like an exponential, so I'll just tack in an exponential. Maybe that's fine. Maybe it's fine to have like 15 fire models. I don't know. There's something that you can say like works computationally is optimal, but there's also something that says for like, okay, this will get the job done.
No, I don't see why there is a problem. If you have a global machine learning model which is trained on global properties, the predictors are global, they will have the machine learning algorithm will be able to pick up these different relationships regionally. So it will recognize that in the Western US is wind-driven, whereas, for example, in Central Europe is, I don't know, moisture-driven, and saying things now. Wouldn't that be theoretically possible? Unless you are missing a process you don't have at all in your model, which might be important, I don't know, in Southern Europe, for example.
In principle, you're absolutely correct. This should happen, except it turns out that there could be confounders, right? So, like exactly with the natural and the human case, you could have a region where human ignitions or like human suppression is really important, whereas another region it's not, and the machine will learn some form of average, and so that'll just like not be the right physics, so to speak.
But theoretically, you can put it in. If you had it in, if you had all the processes in,
Yeah.
a global model should be able. Shouldn't you be able to build a global machine learning model?
In principle, sure. Yeah. Right. So what does my model look like in practice? It's a fairly simple model, but I think it was simple enough to actually do some things, to do some interesting physics-based insights onto it. So what I do is I take like a simple multi-layer perceptron. So if you just remove the final layer, you can think of this as your classic neural network. There's some input nodes. It goes the direction you should be looking at is down to up. You have some hidden layers. These are composed, and they have some nonlinear activation functions. And the outputs usually are, well, you have one output depending on the variable that you're interested in. So if you're interested in fire frequencies, you say L output whether there's a fire or not, or like the probability of whether there's a fire or not. Or in case of the burned area, you just output the size of the area. And it turns out that whatever you predict in the last layer is dictated by something called the loss function. So the simplest loss function that you can think of is the mean squared loss, or the mean squared error. Turns out that secretly what you're doing is you're imposing a Gaussian likelihood. And so if you start from that and you work backwards, it turns out that what is actually best to output in this case, given that I've been hammering about stochastic processes, are the parameters of a statistical distribution, or to be more accurate in this case, a mixture of these distributions, just to give you more flexibility. And so my general loss function here looks like a product over all the samples that I'm taking. And for each sample, I have a mixture distribution, which is just the linear sum of different statistical distributions. And I'll talk about which distribution. It depends on whether the response variable that you're interested in is frequency or size, under the constraint that the different mixture components sum up to 1. What does this mean? Well, it just means that I could be parameterizing all the different grid cells. So these are about 30,000 grid cells in my site, not accounting for the fact that there's time, but okay, just 30,000 grid cells. In principle, it could mean that I have 30,000 parameters, so one parameter for each grid cell. But the machine learning in the nutshell, the dimensionality reduction in a nutshell, is the fact that the independent parameters here are just the weights of my neural network. So even though ostensibly I'm learning like these different parameters, so if you can think of the statistical distribution where y is the response and theta is the parameter as a function of the inputs, which are the x. In principle, you can think of learning 30,000 parameters, one for each grid cell, but really what you're training are the 1,000 odd parameters of the neural network itself. So these are the population parameters that you're learning, which will result in different sort of parameters for individual parameters for the grid cells. But these are not strictly independent. Right? And so this is just to learn that at some level, the physics between the fire in different grid cells is shared, and that is encoded in the neural network. So this is just to say that, like, it has many free parameters, about 1,000, which is a lot, but it's not it's still not as high as the number of, like, it's not treating each fire independently or each grid cell independently. And so what I do is I create two models. I create one model for the frequency, one model for the size. The frequency model is a zero-inflated Poisson distribution. It turns out that in some limit you can think about this as a Poisson process, but for the moment it's just a zero-inflated Poisson distribution where I'm taking the inputs and I'm learning, by optimizing this neural network, I'm learning the rate, the dispersion, and the weight for each component. And what the zero-inflated does is that it adds a separate weight to a zero process. So it turns out that because there's many grid cells with no fires is a rare process, you'd want to account for the fact that you can see excess zeros that may not reflect the fact that this is due to weather conditions. So for instance, if humans are proactive in reducing fires, it means that you won't see a fire, but you want to account for the fact that despite the fact that there were fire-like conditions, we did not see a fire because there was some suppression. So you add a separate weight component for that. For the fire size, you again consider a mixture distribution, and it turns out that fire sizes typically follow a long tail. So you use a generalized Pareto distribution or a log normal distribution, and you learn the parameters of these distributions. But you also have to account for the fact that, as I mentioned, the Dixie fire and the August complex fires, these are just large fires. So you just need to ensure that depending on the size, your model sees many more examples of these than are actually in the data, right? And so this accounts for the fact that you can you still perform reasonably well at large fires through this reweighting. And finally, what you do once you learn these parameters for all the grid cells, you do the same process that I mentioned earlier, which is for each grid cell, you go and you ask the question, is there a fire or not? And you do this by sampling from this statistical distribution with the parameters fixed to their optimal values determined by the network. Then you multiply by the total number of fire counts, and then for each fire or each fire that you get in these draws, you draw a size of that fire from this statistical distribution, which is the size distribution, with again the parameters fixed to their optimal values, and then you consider the mean and the variance of this distribution. So this is the stochasticity at two levels. One is you have a distribution to initiate a fire, and once you have fires, depending on what fires you have, you draw the sizes of the distribution, and you do this over like 1,000 runs, and you do this with Monte Carlo. So I don't calculate this. It's effectively doing an integral, but I discretize it by doing a sum. And similarly, I calculate the variance. There's some model training and cross-validation procedure. To keep it short, what I'll say is I do the 70-30 split of all fires between 84 and 2019 as training and validation. And so these are randomly selected in time and space.
What does it mean? What does it mean, 70-30 split?
Just so I select 70% of all the fires between 84 and 2019 as training and leave 30% as validation. So these are fires that the model doesn't see in training. For the test data, I consider all fires in 2020. So which is just to say that the fires not seen by the machine learning model are the 30% validation as well as the test. So this is what it doesn't see. And then in terms of like what do you actually show in the paper, in terms of like how do you pick the best model, I use the leave one out cross validation score, which is I calculate the average validation accuracy using this metric, and this metric is a form of KL divergence, except instead of the PDFs, I consider the CDFs, because the PDFs there is no true PDF access, so you just consider the empirical CDF, and and I can get into asymptotic properties of this metric, but for the moment, I consider the leave one out cross-validation score by considering the average validation accuracy of all subsets that I've created by leaving 1 year out. So I leave 1 year out. So I start with 84, so I leave 84 out, consider 85 to 2020, do a 70-30 split, and calculate the validation accuracy of the model on the 30% withheld. And then I do this for every year and until 2020, and I take the average of all validation accuracies. And it turns out that in the frequency case, these are some hyperparameters for which you get the lowest loss, and the highest accuracy. And for these are the hyperparameters. So I should say the hyperparameters are just the number of layers, number of neurons per layer, and the number of components in the mixture distribution. And the generalized Pareto gives again the lowest loss and the highest accuracy. And you'd be like, well, what happens? Well, okay, here it's just the test data is just all fires in 2020. It turns out that if I leave out 3 years of data, besides the train validation, there is a decline in performance, but it's only marginal. So it's not as if like the machine learning model has worked best on this configuration, and anything short of this, it fails. There's some decline, but until 3 years, it's still. I mean, I wish I had this table here, but it goes to around 85 for 3 years, and in case of the size, it goes to 80%. So it's still fairly accurate.
So for more than 3 years, you get very large decline in
accuracy? Yeah. It goes at 5 years, it's 50%. In which case, might as well do a coin toss. Yeah. But this is already to say that it's not just 1 year; it's that 30%. That I think adds in earlier versions of this talk, people will be like, oh, it's just 1 year. And then now I need to emphasize that no, it's actually 1 year plus 30% of the other fires already. Yeah. Okay, so what do the results look like? And I should mention that the performance metrics that I'll be using are just the Pearson correlation coefficient and the chi-square, which is nothing but the squared loss by the uncertainty that my model estimates. So what does this look like? In terms of frequency, and naturally, the frequency looks best when you consider it over the entire Western United States. Blue is observed, orange is modeled, and this is at the monthly level at the top, annual level at the bottom. And you can see that we have very good correlations, both at the monthly and the interannual scale, which is good because you can sometimes, because the data is only at monthly scale, you could have good monthly scale and then, you don't capture some of the annual scales, but this is good. One thing you should notice is that actually starting around 2007 onwards, the model turns out to be over-predicting fires. And in fact, for 2020, it over-predicts fires by a lot. And it turns out it's because if you just look at the climate, well, it was a very hot year, but there were not that many observed fires. And actually, I mean, we ended up writing the paper and it was fine, but this was still something that was at the back of our minds. And it turns out that there's a new data release of the VUMI data set that will come out very soon. And it turns out that there's actually missing fires in the database. Mm-hmm. And this gets into the really gnarly world of like how federal agencies report fires. And it turns out that there's one scientist, Karen Short, who's managing, she has her own database, and that's the one that is trustworthy. Every other database is like has missing fires, has duplicate fires, and it's a little bit of a mess. So in that case, if you're using MODIS data, you're probably doing already a lot better than aggregate data from federal agencies, because you just don't know what's happening. Anyway, I like to think that this is how our model was able to anticipate that there were actually missing fires. But okay, I mean, that's the good part. There are bad parts of the model too. Like for instance, in places like Sierra Nevada, it doesn't, it cannot get the seasonal cycles for a long time, so it misses the fires here. Part of it is because Sierra Nevada doesn't see that many fires as compared to, say, the Northern Great Plains and the Intermountain Desert. which sees a lot more fires and there's a more regular activity. For the Pacific Northwest, it was interesting that it can sometimes also do this thing where it just misses the peak of like the fire. Like, so there's a peak in about 2001 or 2002 or 2001, and then it did the peak in 2003 instead. And so that, I think, was something not quite. It was not. Yeah, it was a weakness of the model.
They also missed the low point before that. So
That's right.
Before the peak.
That's right. That's right. Exactly. Yeah. And even here too, right? It did not guess that. So yeah, this is one of those things which we need to look at more closely in terms of, okay, it's a simple counts model. You should be able to get this right. Part of it is ignitions, like hard to get ignitions unless you have a physical process, and humans are weird. We ignite, randomly, so to speak. But yeah, so this is, and there, of course, there's results for other ecoregions, but I'll only show this here in the interest of time. But again, I want to emphasize that the model is built at the grid scale level, and I'm showing results here at the aggregate level because it just looks prettier. And of course, it beats down the noise, but okay. For fire size, it's, we had to do some adjustment for the fact that it turns out that this is actually, while we were finishing up this paper, there's a paper that came out in Science Advances in 2022 by Virginia Iglesias and Jennifer Balch, which basically talks about the fact that if you look at the aggregate size distribution of fires between 84 and 2004, just about, you can move the data a little bit in terms of year, and you look at the fire size distribution after that, so from 2004 to 2020, these are very different. And so this goes into the conversation about fire regimes, right? And so in terms of our plot, I show this by so if I were to zoom in, but if you look at the dotted red line, which is 84 to 2004, and the dashed red line, which is 2005 to 2020, you see that the complementary CDF, so this is just 1 minus the CDF, and on the y-axis, it's the fire size in kilometers. These are really different, like just observations, not even modeling. And so it turns out that we needed to do this reweighting using the factor that I mentioned in my likelihood. We basically needed two different distributions for the generalized Pareto case. So we needed one for 84 to 2004 and the other for 2005 to 2020. And then if you add them up, boom, you get the total observed. So this is also something that I found, that if you want to get the full temporal trend right, you'd also want to account for the fact that there could be vegetation-based regime shifts, because, or it could just be that, the 90s were dry, and so the vegetation, just responded more strongly to dry weather in the 2000s. And this is where I think physical models will really help. So if they're able to catch this weather vegetation interaction correctly, then you'll just be able to sort of encode this into the moisture relation and so on, which is missing using statistical models. For fire size, we get good results as well. I should say that on the left-hand side, the plots that we've made are, again, for the monthly area burn and the annual area burn. Red is observed, green is modeled, and here the uncertainty band is clearer because it's 68%, but because these are long tail distributions, you have a sizable 68% uncertainty. It turns out that there's two ways you can compare your model results with observations. One, you can use the frequency that you observe, that you observe out in nature in the true distribution, in which case it's a more apples to apples comparison of the fire sizes, because like I said, my model has two steps. One is the frequency model, and then there's the size model. And so just to compare the size model, here in the left-hand side plot, we've used the frequency that is observed. And so no wonder it gets a lot of the temporal effects right. But it was still reassuring to see that, well, yeah, we were able to get things right. Except in 2020, not only were there more extreme fires where our model did not do that well, but as I mentioned earlier, like we also did not get enough frequencies, so we missed the total area burn. And I should say that it's not just a matter of like getting the frequency right in terms of small fires, but also for the large fires. So this is I think there were two effects that were driving the fact that our model did not perform well in 2020. Like we missed some of the large fires, but we also missed some fires in the data set already. But what happens if we include the machine learning frequency? So, have the machine learning predict the frequency, and then use the size model. And again, here you can have just the frequency, but you can also, the frequency is of course an aggregate over space, right? But then you can also have where exactly the fire occurred, because individual grid cells can have their own weather. So again, we did this slightly rigorous test, but like the fact that you can have the frequency predicted by the machine learning model, but you can use observed locations of where the fire happened, and you get great results, including the fact that because our machine learning frequency had more fires in 2020, it produced it gave us the 2020 observed fire sizes. But again, it's a case of is this the right answer for the wrong reasons? But then you can also use observed frequency, so that's the counts. But then you can use the locations predicted by the machine learning model, and it turns out that and you can already see in this 92 to 2004 region, the machine learning model chose locations for fires that corresponded to locations which had the highest VPD, for instance. And that turns out that actually, most fires did not happen at those high locations. So you got artificially inflated fire sizes. But then you can also do both frequency and locations, and then you do agree at the latter half. So this after 2004 looks good, but before 2004 it doesn't look that good. And so this is just to tease out the fact that there's different scales at which the fires are happening. So you can get the frequency right, but even if you get the locations wrong, that could also result in a discrepancy with the observed fire sizes. And this is true, I would say, independently of what model you're using. And yeah, you can play this game for the different ecoregions as well. And yeah, 2020 was definitely something that we missed for Sierra Nevada and Pacific Northwest. And I should say that you can always do. I mean, and we did this. We included 2020 as part of the training data set and left out another year, and our models still have trouble getting the 2020 because it's just such an outlier as compared to the rest of the fires.
Are there just very anomalous things, like when you're getting these summer thunderstorms in California, things like that I don't know, I don't remember seeing that much of, but certainly seem to impact fires a lot.
Yeah, they do, and this is also one of the, I guess, inadequacies of you doing monthly scale, having monthly scale climate variables. We are not modeling fire spread, and I think there's a lot of stochasticity in how exactly if you have a thunderstorm, if you have a summer storm, and also subtle things you could have a huge rainfall event while a fire is growing, and so just the sequence of fire growth and then rainfall that terminates its growth, not present in our model at all. So this is something where if you're thinking of emulating fire behavior, there should be a small, I would think that you can think of it as a high fidelity model that if you have certain extreme conditions, you use this high fidelity model that models fire spread and then accounts for these, thunderstorm effects. And yeah, this is just to sort of emphasize the point that 2020 was really anomalous, even as compared to other anomalous fire seasons in terms of burned area, and that was purely because you had just these spectacularly large fires. and which the mean state model just completely missed. And so if you look at the observed annual error burned in 2020, it's at the 99.5th percentile of what our model would anticipate. And it's mostly driven by forests, and particularly the Sierra Nevada and the Pacific Northwest. Whereas in, say, 2012 and even 2017, most of the fires were, well, in 2017 it was forests, but in 2012 it was the desert regions. So there we're able to get this activity right. But if it's happening in forests, and this goes to the other part where there's been a lot of work that shows needs to be slightly rigorous in my opinion, but like shows that there's been a legacy or like a century of fire suppression, and that's just resulted in a lot of like built up fuel. So modeling that is a little hard, but that if there was one data point that at least seems to agree with that hypothesis, it's this one, that in 2020 it's just went to the 99.5th percentile. And to Marcus's point, I should also say that one thing that we observed, if you just compare, in blue we have the distribution of small fires, and in yellow we have large fires, and I have some legends here for different fires, unimportant at this point, but essentially you can see between small and large fires as a function of different variables, say VPD, fire weather index, and the 1,000-hour fuel moisture. You can see that there's a statistical difference between these distributions between small and large fires. But if you look at just the large fires between 84 and 2019 and 2020, well, the 2020 being in yellow and the 84 to 2019 being blue, actually we did not even have that many extremes in 2020, at least at the monthly scale, right? And these are just because these are monthly scale variables. So clearly, like, I mean, the model doesn't work in the fact that, yes, it doesn't produce these large fires, but I mean, there's a reason for it, because you don't have at the monthly scale variables that are as extreme as fires in the past. So, and I think I should stop in 5 minutes or so, but I want to just...
Can I interrupt for a minute?
Yeah.
So I was wondering, it's no secret that the machine learning and any AI system is as good as the information you provided, right?
Yep.
So should we stop hoping that we'll be able to simulate, in that sense, extreme events, fires included?
Can you say more? I mean, I have an answer, but could you?
Yeah.
Could you
So if we don't have frequent extreme fires, which is exactly the definition of extreme fires, they are not frequent, then the machine will not be trained for them, and then it will not be able to simulate them. So should we lose hope?
I mean, maybe at aggregate scales, this will be a hard problem, like at the scales that I'm working on, which are monthly scales. But there are fire models that work at much smaller scales. And these are actually coupled fire atmosphere models, like wildfire, for instance, which might have a better case. Actually, they could not even, like, even they have the deficiencies. But if you were to apply, some form of machine learning enhanced, but not that machine learning has all the answers. But if you were to improve those models in various ways, they could be a better bet for predicting extreme behavior, because it's extreme. You can think of this as rolling die, right? And I think you're basically hinting at that, which is, like, for a fire to become an extreme fire, like 6 things need to happen. So 6 die need to be rolled, right? So it's necessarily rare, which may be hard for like an aggregate model that aims to do everything, like, at a more regional or even like a global scale. Whereas if you have like these specialized models for fire spread, and these are used for operational, so where to handle fire suppression resources, those models could still have a chance. I'm not an expert, so I'll just say I don't want to shut the door on those models. They clearly are very interesting and need work.
Thanks.
Yeah, but it'll be hard for these aggregate models. So just to in towards concluding, I want to highlight what I do for ultimately, and this is a question that Marcus asked earlier, which is there is a way to build a machine learning model and account for correlations and have predict the responses. But then this is one of the major drawbacks, I would say, of machine learning models is how do you assess the importance a posteriori? And it turns out that there are methods in the literature that have been developed to do this. One of the most popular is the Shapley additive explanations. And an intuitive way of thinking about this is to think about this figure, but just in reverse. So you can think of these as three robots that collectively produce this much value or some credit or some score. And then you play this game in reverse to assess what is the contribution of individual robots, or in this case, individual predictors. And how do you do this? Well, you consider coalitions of these two robots and say, what is the individual contribution for each of these? In terms of an equation, what this means is that you consider all permutations of coalition with a predictor and without a predictor, and you just divide by, by the weighted, you consider the weighted sum of these values, and that gives you the Shapley value. And I want to say that part of the reason why this predictor importance value really is very popular is because there's a Python package that is publicly available.
Everybody uses it.
Everybody uses it. If you like, it's a whole separate talk talking about like what are predictor importance methods and what are its drawbacks, because there are drawbacks. And to Marcus's point earlier, can it handle correlated variables? In principle, sure. In practice, in this kernel explainer package, no. Because it has to make computational simplifications. It's a combinatorically hard problem. So, yeah. Anyway, with that caveat aside, this is what we find in terms of important features for frequency and size for the mixture density network. And I show this for the entire West United States, forests and deserts. And of course, I can make these plots for each different ecoregion as well. The way to read these plots is orange. The more orange you get, what it means is the higher the value of the variable, in this case VPD, the more orange it is. And so what this means is the higher the value of the VPD, the higher its contribution to the fire frequency, right? And similarly, if it's blue or purple, you should think of this as this is fuel moisture, the 1,000 hour fuel moisture. So lower the fuel moisture, the higher the likelihood of fire frequency. And it turns out that, well, there is more or less the most important variables for fire frequency, at least, are hot and dry conditions. And this is true both for forests and deserts. But if you go lower down the list, you start seeing interesting things. You start seeing, for instance, as Anastasia was mentioning earlier, was what about antecedent precipitation, the 1 year lag? It turns out that for deserts, there are dual effects, you're right. But like for deserts, it's higher the precipitation, it turns out that higher the fire frequency in the lag 1 year. Lightning also is an important predictor, and this is it shows up in deserts and forests because of course that's connected to. So this is just the strike density, so it correlates with the likelihood of ignitions. But one major difference, of course, is that in deserts the fraction of grassland is very important, whereas in forests it's in fact it has lower importance. And similarly for fire size, grassland is one of the more important variables on the vegetation side for deserts, and whereas for forests, its biomass also has an important role to play. And similarly, these indices show up. So to your point earlier, is this index in principle a machine learning model should be creating its own index? Yes, it kind of does that, also including the index that we currently have as a recipe. And so one of the things that this index doesn't have is T minimum. And so this is something that we found like recently, like the minimum temperature is just much higher, and that leads to more fire spread. Well, the advantages of SHAP is also you can do this functional relationship between the predictor and the SHAP value. And it turns out that in case of frequency, there's a linear relationship with VPD, but in case of and this is in forests, whereas for size, it is it's almost exponential. So this is something other people have shown too, including Park and his grad student, but this is something that our model is able to pick up, like through this explanation procedure, which is flawed. But the machine learning here is, the machine learning model is clearly learning something. It's not garbage. And so one can go into details, and this is worth going into, but at the end of the day, it is fairly robust. If you do all the steps right, you know. I think I'll skip this for today, but there's some work that I'm doing on seasonal and subseasonal forecasting, where I think, you know, currently it is a fully statistical model, and something that I'm interested in doing is, especially because it's very hard to get the precipitation variability right, even at monthly scales, I'd say 2 months out. Next step is to use NMME outputs or like climate model outputs for doing seasonal forecasts. But yeah, I think I'll just summarize my results for now, which is that I introduced a machine learning based framework. The results are available in this paper. We are able to achieve reasonably good temporal correlations for fire frequencies and sizes, and this is across different ecoregions. So it's not that, you know, it works best in a certain ecoregion. There's reasonably good performance across all ecoregions, provided they have a certain number of fires. So if you have 10 fires, well, you know, in an ecoregion, it won't do that well. But and yeah, the rest of them are for like the subseasonal forecast.
Thank you.
So if you've done your seasonal prediction for 2020.
Well, I can show you the one for 2022. For 2020, it'd be interesting. And it turns out that this is something that we had done last year around May, and we were able to get this New Mexico fires and fire distribution correctly. But this is for June to September, and it turns out that we were predicting a lot more burned area in California. That just did not happen because the rains arrived, and so especially towards the end. And so this is always going to be a challenge. And so I think, you know, one thing that we are currently investigating is what's the best way to show uncertainty. Like, so there's the fire model uncertainty, the stochastic uncertainty, but then there's also the climate model uncertainty, and just knowing where, you know, like you'll be in this whole scheme of things. That I think is a plot that we have in our minds. It's not on paper yet, or like on a digital paper yet. So that's where we're at. But yeah, it would be nice to do 2020, see where we are at, and I feel like at this point there are some interesting directions to take in terms of just maybe doing just a case study of like 10 major fires or like 10 major like fire seasons. Maybe connecting, something that I'm interested in doing is to connect it to different parts of the world. And this is why I feel like the global thing is interesting, is what do you do when you just take this model out of the box, maybe, you know, reduce the number of predictors, maybe do 10 that you can find in, say, Australia or in Western Europe, which is seeing, or in Spain or like southern France. How good or bad does this model do? Unclear.
Sorry, I think I have to run to the next meeting, and I'm connected to the owl, so we may have to say goodbye to whoever's online, which I think is just Maggie at this point. I think people jumped off.
Yeah,
Maggie,
it's just me.
okay.
So
Do
no
you have any
worries.
questions before we, or can I shut this off?
No, you can shut it off. Jatan, this was really cool and interesting. So thank you for coming and for staying a little longer and talking about your work.
Yeah.
Thank you for having me, and I hope you feel better soon.
Thank you. Yeah, hopefully. Bye.
Bye-bye, Maggie. And people are welcome to continue the conversation. I just had to shut Discord off.
Okay. Thank you.
Thank
Appreciate
you.
Appreciate the help.
Sorry.
Did you?
Yeah.